Hello, ladies and gentlemen. My name is Chenhong Zhou. It's my honor to present our paper, Adaptive Status Report with Congestion Control in NB-IoT on this conference. The presentation today is divided into 4 parts. Firstly, the background will be introduced in introduction part, as well as the target of this paper. Secondly, our proposed algorithm, polling TCPW, will be presented. In order to illustrate the effectiveness of the method, simulation results will be shown afterward. In the end, I will conclude our paper and talk about our future work. The Narrowband Internet of Things, NB-IoT, has attracted much attention due to its low power consumption, wide coverage, multiple connectivity, and other characteristics. Accordingly, it has great commercial value in meter reading, sensor monitoring, and other services. NB-IoT protocol is divided into 2 planes. In both planes, the radio link control (ILC) layer is responsible for grouping and concatenation of ILC service data units (SDUs) to meet the requirements of data transmission, and for the reorganization and decomposition of the ILC protocol data units (PDUs) received by peers. In addition, the sliding window method is used in ILC to sort data packets, and the automatic repeat request (ARQ) retransmission of data packets is realized through ILC status reports. The length of ILC PDUs is indicated by the Media Access Control (MAC) layer, and the size of the sliding window and the maximum number of retransmissions are configured by Radio Resource Control (RRC) layer. This is the workflow of ILC protocol under acknowledged mode, which is called AM mode. Therefore, data transmission in NB-IoT is basically completed by the ILC layer. At present, the network delay of NB-IoT can be as much as 10 seconds, which prevents its use in time-critical applications such as intelligent parking and fire detection. Hence, optimizing the ILC parameter configuration to improve NB-IoT data transmission performance has become a new area of research. In 2009, Zhao proposed the hybrid automatic repeat request (HARQ) between ILC and MAC layers. In 2014, Liu put forward parameter optimization methods, such as optimizing the number of PDUs in the ILC layer. In 2016, Ritesh improved system transmission efficiency through the dynamic selection of ILC modes. In 2018, Kumar dynamically adjusted the size of the ILC cage according to feedbacks on transmission delay. The above optimization algorithms improve data transmission efficiency to a certain extent, but changes in network resources are not considered in all of them. In narrowband conditions, if a large number of terminals carry out transmission services at the same time, network congestion can be caused due to the wireless resources being insufficient. This can lead to congestion of the sliding window, which has an impact on communications in NB-IoT. In order to solve this problem, an adaptive sliding window algorithm, polling TCPW, is proposed for the IoC protocol based on the improved TCP westward congestion algorithm in the TCP communication protocol. Our algorithm is based on the TCP/W congestion control algorithm. The picture shows the workflow of TCP/W algorithm. The maximum number of data packets to be transmitted in each round equals to the CWND value. The CWND is doubled every time an acknowledged ACK reply is received. Otherwise, the slow start threshold SS thresh is halved and the CWND is set to 1 to start the congestion avoidance algorithm. When CWND is not smaller than SS thresh, the congestion avoidance algorithm is started with an initial SS thresh value of 16. After entering the congestion avoidance phase, CWND is increased by 1 if there is no packet loss and the retransmit timer is running. Otherwise, SS thresh is modified by the equation. The TCP/W algorithm provides fairness and improves the throughput of the wireless network. However, the initial value of SS thresh in the slow start algorithm lacks a theoretical basis, and the growth rate of CWND in the congestion avoidance algorithm cannot guarantee the speed of the system's response. In addition, TCP/W cannot distinguish between losses caused by channel quality and link congestion, which makes the system call the slow start algorithm frequently and reduces the system's performance. In order to apply TCP/W congestion control algorithm in IoC protocol, we combined status reports with congestion mechanism. The workflow of polling TCP/W is shown in the picture. Firstly, single ACK or NACK is replaced by status reports, which can improve the TCP/W algorithm by determining the reasons why status reports are triggered. Secondly, CWND is adjusted according to the current network's available resources, judged by the RTT value. Thirdly, congestion parameters are modified according to the causes of the status report. Finally, status report can be reasonably generated due to the adaptive value of the timers. These four aspects can optimize the TCP/W algorithm and avoid congestion as well as decrease transmission delay in IoC protocol. We use STM32F103 RCT6 as the hardware test platform, acting as both sending and receiving entities. The transmission channel was simulated in MATLAB and communications were carried out through USART. This is the sketch map of our design. In order to demonstrate our algorithms in IoC protocol, we simulated and analyzed the standard IoC protocol and an IoC layer protocol incorporating the polling TCP/W algorithm in terms of delay, throughput, and the blocking probability of the sliding window. For an IoC SDU of 30 bytes, the average delay between generating an IoC PDU in the transmitter to passing it into an IoC SDU in the receiver is shown in the picture. Under different conditions of PDU loss rate, our proposed algorithm reduced more than 15 milliseconds than the standard IoC protocol stack. When the rate of packet loss increases, the delay of the proposed algorithm increases slowly, while that in the standard IoC protocol stack increases rapidly. When the loss rate reaches 0.3, the delay in the standard IOC protocol stack is about 473 milliseconds, while the delay of polling TCPW is less than half of it. This result indicates that the polling TCPW algorithm can reduce the delay of an IOC protocol stack. Under the condition of zero data loss, we record the number of bits of data processed by the receiver within 60 seconds from the startup of the device with different PDU lengths. As the results show, the throughput of an IOC protocol stack using the polling TCPW adaptive algorithm is more than 1000 bps higher, sometimes even 2000 bps higher than that of a standard protocol stack. The result indicates that the polling TCPW algorithm can improve the throughput of an IOC protocol stack. The blocking rate of sliding window P is defined in the equation. N is the number of IOC PDUs transmitted, and window length is the sliding window length. Under different PDU loss rates, P is averaged from multiple tests. When the rate of packet loss is less than 0.5, the blocking rate of the optimized sliding window is similar to that of the standard sliding window. When the packet loss rate is greater than 0.5, the blocking rate of the adaptive sliding window increases steadily, while the blocking rate of the standard sliding window increases significantly. This result indicates that the polling TCPW algorithm can deal with changes in network resources effectively, and the robustness of the system can be improved. To conclude, this paper proposes an adaptive sliding window algorithm, polling TCPW, based on the improved TCPW congestion control algorithm. The TCPW algorithm is optimized by utilizing status reports, modifying CWND according to RTT value, and calculating RTT depending on the causes of the status report. The sliding window mechanism of IOC is optimized by adaptively adjusting values of timers according to the parameters of the congestion control algorithms, such as RTT and CWND. As the simulation results show, our proposed polling TCPW algorithm can effectively improve the throughput of the protocol stack and reduce transmission delay on the basis of guaranteeing the stability of the system. Due to hardware platform limitations, this paper only simulates the IOC layer protocol applying polling TCPW. As the reviewers' opinions say, this is a limitation of the solution proposed. So in the future, a more accurate investigation will be done considering more general scenarios on OAI platform. What's more, a complete NB-IoT protocol incorporating polling TCPW will be verified. Thank you for watching and listening. We wish the conference a great success and wish you to have a great time. Thank you.